So recently I received questions in the comment section of a video that belongs to my multi-threading series. A Mr. named Rod Mohammed, did I speak that name correctly? Chances are that my phonetic capabilities reach a limit here, so feel free to correct me if I'm wrong. Anyway, the questions were about Java RMI and sockets. The first question was how data is transferred when both sender and receiver are using Java. And the second question was, what happens when either the sender or the receiver is not running Java? How does communication work then? And what are the limitations or alternatives? So one possibility would be to write a huge text in the comment section and hopefully providing all the answers. But I found this topic quite interesting, and therefore though, why not create a video about this? So here we go, let's tackle these questions step by step. To give an approximate structure of this video, let's list the covered topic parts and questions we seek answers for. As we cannot guarantee that everybody knows about Java RMI, let's cover first what that is. The questions also address sockets. Same thing, let's also make sure we know what that is. As the questions range around both of these topics, let's also make sure what Java RMI and sockets have in common. At this point, we may want to check out a practical example to see Java RMI in action. So let's build a client-server example in Java. To cover both topics practically, let's also make sure we see Java in action with sockets. We now have the foundation for both of these technologies, and because of this knowledge, we are now ready to challenge us a bit to find out if applications built with different programming languages can communicate over RMI or sockets. Alright, let's dive into what Java RMI is all about. So RMI stands for Remote Method Invocation, and at its heart it's a Java API that lets you call methods on Java objects that are running in a different Java virtual machine, or JVM, than the one your code is currently running on. Think of it as making a phone call to an object that lives somewhere else. To make this magic happen, RMI uses a few key players. First you have the remote interface. This is like a contract that defines the methods that can be called remotely. It's a regular Java interface, but with a special marker, it extends Java RMI remote. Also, any method declared in this interface needs to be prepared to throw a remote exception, because, well, things can go wrong when you're talking across a network. Then, on the server side, you have a remote object implementation. This is a regular Java class that actually implements the remote interface and provides the real logic for those methods. Often, this class will extend unicast remote object to handle the networking details, although there are other ways to do it. Now, how does this client actually interact with this remote object? That's where the stub, also known as the proxy, comes in. This is a client-side object that pretends to be a remote object. It implements the same remote interface from the client's perspective. It looks and feels just like the real thing. When the client calls a method on the stub's job is to package up that call, the method name, the arguments, and send it over the network to the server. This process of converting objects into a stream of bytes for network transmission is called marshalling. On the server side, back in the day, there was something called a skeleton, also known as a dispatcher. Its main role was to receive the marshal call from the client, unpack it, a process called unmarshalling, and then actually invoke the corresponding method on the real remote object. Nowadays, the skeleton's functionality is largely handled internally by the RMI system itself, so you don't see it explicitly as much. To keep track of all these remote objects, there's an RMI registry. Think of it as a phone book on a server. When a server starts up, it registers a remote object with the registry, giving them a name. Clients can look up these remote objects in the registry by their name and get back a reference to the stub. Underneath all of this, there's a transport layer, which handles the actual network communication, typically using TCP/IP, the workhorse of the internet. And then there's the remote reference layer, which takes care of managing references to those remote objects and the semantics of how those remote invocations happen. So, putting it all together, the server plays the role of the host. It creates the remote objects, implementing their logic, and then registers them with the RMI registry, basically saying, hey, I've got these services available. The client, on the other hand, acts as a consumer. It contacts the RMI registry on the server, looks up the remote object it needs, and gets back a stub. From that point on, the client can just call methods on the stub as if it were a local object. The working progress goes something like this. The server registers its objects. The client looks it up in the registry and gets the stub. When the client calls the method on the stub marshals the call and sends it across the network. On the server, the RMI system unmarshals the call, invokes the method on the actual remote object, and then marshals the result back. This marshaled result travels back to the client stub, which unmarshals it and finally returns it to the client-side's code. Now, why would you want to use RMI? Well, it has some advantages. It's very object-oriented, allowing you to work with objects across different JVMs in a natural way. It supports mobile behavior, meaning you can even pass objects by value between JVMs. It can facilitate various design patterns for distributed systems. It has built-in security features, and for Java-based systems, it's relatively simple to set up. Plus, because it's Java-based, it's generally platform-independent as long as you have a JVM. It even handles distributed garbage collection, so you don't have to worry about manually cleaning up remote object references. It also supports concurrency, allowing multiple clients to interact with remote objects simultaneously, and even has the potential for integration with non-Java systems, although that's where things get a bit trickier. However, it's not all sunshine and rainbows. RMI does have its disadvantages. The biggest one is its Java dependency. Both the client and the server pretty much need to be running on a JVM, which leads to a tight coupling with the JVM. There can also be potential security risks if not configured properly, and in some complex scenarios it can become quite complex to manage. Firewall issues can also arise because of the dynamic ports RMI sometimes uses. Crucially, there's no standard for non-Java clients to directly interact with RMI services, and in many modern scenarios, RMI has been somewhat superseded by other technologies like RESTful web services, for instance. So, when would you typically use RMI? Well, it's often used in Java-centric distributed applications, where you have both the client and the server written in Java. It's also suitable for client-server systems within Java environments and applications that need to transfer complex Java objects between JVMs. At its core, the core function of Java RMI is to enable distributed Java applications through remote object communication, making it feel like you're working with local objects, even though they might be running miles away. Now, let's touch on why RMI isn't exactly the go-to solution for communicating with applications built in other programming languages. There are several key reasons for this. First and foremost, Java object serialization dependency. RMI relies heavy on Java's specific way of converting objects into a stream of bytes, Java serialization. This format is very specific to Java and isn't directly understood by other languages' object model. Secondly, there is a deep JVM integration. RMI is tightly woven into the JVM features like class loading, reflection, and its own distributed garbage collection mechanisms. Replicating all of this in another language to achieve seamless RMI compatibility would be incredibly complex. Then you have the remote object reference management. RMI has its own way of keeping track of remote object references, which is closely tied to the JVM's concept of object identity and its garbage collection process. This isn't something that translates easily to other language environments. The process of stub and skeleton generation, or creating their equivalents in other languages, is also geared towards Java classes and the RMI protocol. You'd have to essentially build a similar mechanism in the other language to handle the proxying and dispatching of remote calls in a way that RMI respects. Furthermore, type system compatibility is a significant hurdle. RMI leverages Java's strong typing, ensuring that data types are correctly translated, and consistent between Java type system and another language's type system can be quite challenging and error-prone. Finally, the practical complexity of trying to fully implement RMI compatibility in a non-Java language is immense. It would likely be far more efficient and practical to use other, more interoperable protocols and data formats that are designed for cross-language communication, like JSON or XML over HTTP. So, while in theory you might be able to build some level of communication between a Java RMI service and a non-Java application, the reality is that it would be a very involved and likely inefficient undertaking due to RMI's deep Java-specific nature. Alright, let's switch gears and talk about sockets. Now, unlike RMI, which is very Java-specific, sockets are a much more fundamental concept in networking. Think of them as the basic building blocks for communication between different applications across the network, regardless of the programming language they are written in or the operating system they are running on. At its core, the socket is an endpoint of a two-way communication link between two programs running on a network. It's like an electrical socket. You plug something in at one end and something else at the other, and you can then exchange electrically. Or in the case of network sockets, you can exchange data. To establish a connection using sockets, you need two main things: an IP address and a port number. The IP address is like the street address of a house, identifying the specific device on a network. The port number is like an apartment within that house, identifying a specific application or a service on that device. So, a socket address is essentially a combination of an IP address and a port number. There are two main types of sockets you'll encounter: TCP sockets and UDP sockets, where TCP stands for Transmission Control Protocol and UDP stands for User Datagram Protocol. TCP sockets provide a connection-oriented, reliable, and ordered byte stream service. Think of it like managing a phone call. First, you establish a connection with the other party. Once the connection is established, the communication is reliable, meaning if you send data, it's guaranteed to arrive and it will arrive in the same order you sent it. TCP also handles things like error detection and retransmission if data packets get lost along the way. This reliability comes with a bit of an overhead, as the system needs to manage connections and ensure data integrity. TCP is commonly used for applications where data integrity is crucial, such as web browsing mainly with HTTP, email mainly with SMTP, and file transfer where one possible protocol is FTP. On the other hand, UDP sockets offer a connectionless, unreliable, and unordered datagram service. Think of it like sending postcards. You put your message on a postcard and send it off, but there's no guarantee it will arrive. And even if it does, it might not even arrive in the same order as you sent the postcards to. UDP has much less overhead than TCP because it doesn't establish a connection or guarantee delivery. This makes it faster and more efficient for applications where occasional data loss is acceptable or where low latency is more important than guaranteed delivery, such as streaming video or audio, online gaming, and DNS lookups. The typical communication process using sockets involves a client and a server. The server application creates a listening socket on a specific IP address and port number. This is like putting your phone on a hook and waiting for a call. When a client application wants to communicate with the server, it creates its own socket and attempts to establish a connection to the server's IP address and port number. For TCP, this involves a handshake process to establish the connection. For UDP, there's no explicit connection establishment. The client simply sends data packets to the server's address. Once a connection is established in the case of TCP, or the client starts sending data in the case of UDP, data can flow between the clients and the server. The operating system handles the underlying details of packaging and unpackaging the data into network packets, routing them across the network and ensure they reach the correct destination and application. Now, why are sockets so fundamental and widely used? Well, one of their key advantages is their universality. They are a core concept in networking and are supported by virtually every operating system and programming language. This makes them incredibly flexible and allows for communication between applications written in different languages and running on different platforms. They provide a low-level control over network communication, allowing developers to fine-tune how data is sent and received. For TCP, you get reliable and ordered delivery, which is essential for many applications. For UDP, you get speed and efficiency due to the lack of connection overhead. However, there are also disadvantages. Working directly with sockets can be more complex than using higher-level APIs like RMI or web services, as you often need to handle details like connection management, error handling, and data formatting yourself. For TCP, the reliability comes at a cost of overhead, which might not be ideal for all applications. For UDP, the lack of reliability means you might need to implement your own mechanisms for ensuring data integrity if that's important. Dealing with firewalls can sometimes be tricky with sockets, as you might need to ensure the correct ports are open. Use cases for sockets are incredibly broad. They are the foundation for almost all network applications, including web servers and browsers, email clients and servers, file transfer applications, online games, chat applications, and even lower-level network utilities. In a sense, sockets provide a fundamental mechanism for inter-process communication across a network. They abstract away the complexities of the underlying network hardware and protocols, providing a relatively simple interface for applications to send and receive data. While higher-level APIs like RMI build upon sockets to provide more specific functionalities, sockets themselves remain the essential building blocks for networked communication in a vast array of applications and across diverse technological landscapes. They are the lingua franca of network communication. Okay, so we've looked at Java RMI and we've looked at sockets. Now, a natural question arises. What do these two actually have in common? They might seem quite different at first glance, RMI being a Java-centric and sockets being a more universal networking concept, but they do share some fundamental characteristics. First and foremost, both Java RMI and sockets are fundamentally about enabling communication between different processes running on a network. Whether it's two Java applications talking via RMI or a Java application communicating with potentially non-Java applications using sockets. The end goal is to allow these separate programs to exchange information and work together, even if they are on different machines, potentially miles apart. Secondly, both RMI and sockets typically operate within the client-server architectural model. You have one side, the server, which provides some service or resource, and then you have the client, which initiates communication to request that service or access that resource. In RMI, the server exposes remote objects, and the client invokes the methods on them. With sockets, the server listens for incoming connections or datagrams, and the client establishes those connections or sends those datagrams. Thirdly, both are mechanisms for transferring data across a network. RMI does this by marshalling and unmarshalling Java objects, effectively sending the state of an object or method call parameters and return values. Sockets provide a more raw data stream or datagram service, where you're sending and receiving bytes, and it's up to the application layer to interpret what those bytes mean, regardless of the level of abstraction. Data is being moved from one endpoint to another. Perhaps the most crucial, yet often overlooked, commonality is that Java RMI actually uses sockets underneath. RMI is a higher level abstraction. When an RMI stub sends a method invocation to a remote server, or when the server sends a result back, that communication at the transport layer is typically happening over TCP/IP sockets. So, sockets provide the foundational network transport mechanism that RMI builds upon to offer its more specialized remote object capabilities. You can think of sockets as the pipes and RMI as the sophisticated system that uses those pipes to send specifically structured messages representing Java method calls. Furthermore, both are obviously supported and heavily used within the Java ecosystem for building distributed applications. Java provides robust APIs for both the Java RMI package for RMI and the Java Net package with classes like socket, server socket, datagram socket for socket programming. This means Java developers have options depending on their level of abstraction and interoperability they need. Finally, when working with either RMI or sockets in Java, you'll invariably encounter the need for robust exception handling. Network communication is inherently less reliable than local operations. Connections can drop, servers can be unavailable, data can get corrupted. RMI has its remote exception, and socket programming involves handling various I/O exceptions. In both cases, developers need to write code that can gracefully handle these potential network issues. So, to sum it all up, both Java RMI and sockets are about network communication, usually in a client-server fashion, involving data transfer. Crucially, RMI relies on sockets for its underlying transport, and both are integral parts for Java developers, building distributed systems requiring careful attention to error handling. They represent different layers of abstraction for achieving similar goals of inter-process communication. Alright, now that we have a solid understanding of what Java RMI is and how it works conceptually, let's get our hands dirty and see it in action with some actual Java code. In this chapter, we're going to build a very simple client-server application using RMI. This will illustrate the key components we talked about earlier: the remote interface, the remote object implementation, the RMI registry, and how the client looks up and invokes methods on the remote object. We'll start by looking at the code for a server side, where we'll define our remote service and register it. Then we'll switch over to the client-side code to see how we can connect to the service and call its methods as if they were running locally. So fire up your IDE of choice and let's dive into the world of distributed Java objects. Okay, now let's create ourselves an RMI example in Java. So as we use the same file for both the server and the client, we want to differentiate between a couple of parameters that we set when we start the file. So we want to differentiate between server and client. If args length is greater 0, this means we have at least one parameter, meaning we can get the first param from the command line. Let's put it into a string variable. First param from args, place or index number 0 and 2 lowercase. Now we can differentiate between both of them. The first one is server and the second one is client. And in case that we provided something that is neither of them, we print out an error unknown param, and then what we typed, first param, and the format that we want is server or client, and if a client we also want the server name, and that's about it. Now we want to start with the server. For that we create ourselves a new class. Let's call it calculator server.java. Here we want to define one method that we can call. Let's create ourselves a run method, public void run. And the first thing that we want to create is a registry on port 1099. Registry, locate registry, create registry on port 1099. This also requires a try catch, in which we can provide the error could not create registry. Next we want to define what we will actually be able to do. So let's create an interface for that. Remote calculator. It's an interface which extends remote. And we want to be able to add something which takes an A and a B, and it can also throw a remote exception. What we also need is to implement this. So let's create a class calculator impl, which extends unicast remote object, which is in Java RMI server unicast remote object. And we also want to implement our interface remote calculator. So the first thing that we want to do here before implementing anything else is the constructor calculator impl, also being able to throw a remote exception and executing super. Now let's add what we defined in the remote calculator. Here let's start by printing a message. Incoming request for adding A, which is A, and B, which is B. Then let's do that. Int result A plus B. This is the actual work that we do here. And then let's also print the calculation result. Calculation result. And return it. Return result. That's all we have to do here. Now let's go back to the main method and implement that. So the thing that we want to do here is start the server, meaning calculator server, calculator, new calculator, and run. Now let's go back to calculator server and create an instance of the remote object, calculator impl, calculator. And what we also need to do is bind the remote object to the registry with the name. This can be done using the registry bind. Here we define a name. Let's take calculator service and we bind it to calculator. This also requires us to throw another error in which we can provide the error message error name in registry already used for binding. And after having done the binding, we can also print the message, calculator server started. Now let's go back to the main method and implement that. Calculator server, new calculator server, and run it. That's all we have to do for running the server. Now let's create ourselves the functionality for the client. As we have another argument here, let's make sure we have everything. If args length greater than 1. Here we want to get the second param from the command line. Let's call it second param. And let's get it from args index 1 and again to lowercase. And if not, we print an error. Incomplete param client. And what was the format? We want either server or client, and if client, we also want the server name. Alright, the next thing would be to start the client. And that's the functionality we want to build now. So let's create a calculator client for that. And here we also need a run method, public void run, which takes a parameter, server name. And the first thing that we want to do is get the registry on the server's host and port. Registry, locate registry, get registry, server name, and 1099 for the port. For that we need to throw an error. And here we can throw an error. Could not get registry. The next thing that we want to do is look up the remote object by its name. We do that accessing the remote calculator, in which we cast the registry lookup of the calculator service. Here again we need to throw an exception, in which we can provide an error. Could not bind name in registry. And now let's invoke the remote method. Let's define variables. Int a is 5, int b is 3. Now let's also announce what we are doing. Sending request to the server name to add a, which is a, and b, which is b. Now let's do that. Int result, calling the calculator and the add method, providing a and b. And now that we have the result, let's announce it. Response from the server name with the result and result. There we go. That's all we need here. Let's go back to the main method and implement it. Calculator client, new calculator client, and client run, including the second param. So there's one last thing that we want to provide here. In case we have no parameter at all, we want to kindly remind the user that there are a couple of params that can be provided. So let's add an else and print an error, missing param. And the format is either server or client, and if a client, then also the server name. That's about it. Now let's compile all that. I've prepared a script for that. It's in a parent folder and it's called build. So let's execute that. And there we go. Now we have our brand new RMI networking app 1.0 jar. So what I've prepared here are two virtual machines, one for the server and one for the client. They are both in the same network, so they should be able to reach each other. So the only thing that remains now is copy the file on those servers. So let's do that. Let's go to the folder, target. We're going to use SCP to copy the RMI networking app 1.0 jar to VM RMI server, and we copy it to home, Gene, desktop, once for the server and once for the client. And there we go. So let's first start up the server. This can be easily done by using Java parameter jar and then the file. If we provide no parameters, we should get the error message. And there it is, missing param. So let's provide the param, server, and execute it. And there we go. Calculator server started. Now let's go to the client and do exactly the same. Java jar RMI. Here though, we want to provide the client and the server name, which is VM RMI server. Okay, here we got the error, could not bind name in registry. So this means that the name that we provided for the registry is not the same in both. So let's go and check what the error is. Let's first check what we provided for the client. Here it is calculator service. Okay, that seems to be alright. Let's go to the server. And there we see calculator server, which is not correct. Should be service. Alright, so let's compile the file again. Let's copy it again to the server and also to the client. And let's run it again on both ends. And there we go. This time it works. So to compare. Here we have the incoming request for adding A5 and B3. We calculate the result of 8 and send it to the client. And the client receives it. Well, first he sends it to the server, VM RMI server, and then he receives the response from the server with the result of 8. Now, obviously, this is quite a simple example, but I think it's quite a fun and quick way to see how easy it is actually to implement such an RMI functionality in Java. Now, for expanding this calculator, we could also add a multiply, a division, and so on and so forth. The only limit that remains here is imagination. So what we've just seen in the code is a basic but functional example of Java RMI in action. On the server side, we created a remote calculator interface defining the contract of our remote service. In this case, a simple add method. Then we implemented this interface in the calculator impl class, which contains the actual logic for the addition. The calculator server then took the implementation, registered it with the RMI registry under the name calculator service, making it discoverable for clients. On the client side, the calculator client connected to the same RMI registry, looked up the calculator service and received a stub, that local proxy we've talked about. From that point on, calling the add method on the calculator object on the client actually resulted in arguments being marshaled, sent across the network to the server, the add method being executed on the actual calculator impl object, and the result being marshaled back to the client. The client then unmarshaled this result and printed it to the console. This simple example highlights the core steps involved in RMI communication: defining a remote interface, implementing it in a server-side object, registering that object with an RMI registry, and then having the client look up and invoke methods on the remote object through a generated stub. It effectively demonstrates how RMI allows Java objects in different JVMs to communicate and interact with each other as if they were in the same memory space, abstracting away much of the underlying network complexities. Alright, having explored the object-oriented approach of RMI, let's now shift our focus to a more fundamental way Java applications can communicate over a network, using sockets. In this section, we'll delve into the code that demonstrates basic socket communication between a Java-based server and a Java-based client. We'll examine how the server sets up a listening socket to accept incoming connections, and how the client establishes a connection to the server. We'll also see how data is sent and received as stream of bytes between the two applications. This will give us a clear picture of the lower level mechanics of network communication in Java and how sockets provide the foundation for many higher level networking APIs. So let's take a look at the code and see sockets in action. Okay, now let's create ourselves an example for sockets in Java. So just as in the other example, we have a couple of parameters that we want to make use of. So let's create an if args length. If it is bigger than 0, this means we have parameters. If not, we do not. In the case that we do not, we print an error, missing param and a structure, either a server or a client, and if a client, then a server name. All right, and if we have a param, then we can get the first param from the command line, string first param, args index 0 and 2 lower, so that we don't have to care about the same letters in upper or in lowercase. So here we're going to make use of a switch to see if we have a server or a client. And in the case of a client, we check if we have a second param, so more than one param, and if not, we print an error message. Error incomplete param client, and the format that we want, either a server or a client, and if a client, then a server name. And if we have a second param, we can get the second param from the command line, string second param args index 1 and 2 lower. Alright, and when we have the functionality, this is the place where we start the server, and this is the place where we start the client. Now let's implement the server logic. For that, we're going to create a class simple server, which implements a run method, public void run. And the first thing that we want to define for our server is a port number, int port number. And we're going to take 1, 2, 3, 4, 5. So the first thing that we want to do here is create a socket within a try. So try server socket, socket, new server socket, and we provide the port number. And in case something happens, we catch an IO exception, to which we present an error. Could not listen on port number. And let's also get the error message. All right, after having started the socket, let's print a message. Simple server listening on port number. From here, we wait for the client to connect. And if that happens, we open a new socket, client socket, and we use our already established socket to accept. And then we print a message that the client is connected. Client connected. Client socket get inet address. Once that has happened, we receive the input from the client. Input from the client. Here we also make use of try, buffered reader, new buffered reader, new input stream reader, client socket, get input stream. We also need an output, print writer, out, client socket, get output stream, where we say auto flush true. All right. And within here, we define ourselves a string variable for the input line. And here we create ourselves a while loop to read all the lines. Input line in read line, not null. As long as this is the case, we print the message, server received And what did we receive? Well, the input line. We also send a response. Server says, and we respond the input line with uppercase letters. And if there is a buy, we break the loop. Now there can be errors, so let's catch them. There could be an I/O exception. So let's print an error for that. Error handling client and the message for that. And in any case, we also want to close the connection. So let's use finally and close the client sockets. Now that's about it for the server. Let's implement it in the main method. Simple server and run. Now let's implement the functionality for the client. Simple client. Again, we need a public run method. Void run. Take in the parameter of the server name. Here we also define ourselves the port number 12345, and we again make use of try to create a socket with the server name and the port number. Then we also need the possibility for output. Print writer out socket get output stream and set auto flush to true. For the input we use a buffered reader. New input stream reader socket get input stream. And we will also make use of a scanner for the next line, system in. Alright, so in case of an error, we can have the I/O exception. Here we print an error, couldn't get I/O for the connection to server name. Alright, now let's define two string variables, one for the user input and one for the server response. And when we have reached this place, it means we have the connection, meaning that we are connected to server name and port. To walk through all the lines that we receive, we make use of while, which is always true, in which we tell the user enter message or buy to quit. Colon, and this actually is not a new line, it's just a line. Now we get the user input from the scanner next line, and we can send to the server the same user input. Then we read the server response and print it for the user. Server response and server response. And in case there is a buy, user input equals ignore case buy, we break the loop. And this means we are disconnected, which we can also tell to the user. Disconnected from server. Alright, let's go to the main method and implement the client. Simple client, new client, and run with the second param. And in case we do not have a choice for server or client, we also want to provide an error message. Error, unknown param, first param, and we want to provide the format, which is either server or client, and if client, then also a server name. Alright, that's about it. Now let's build the project. Again, in the parent directory. And there we have it. In the target, here we have it, Sockets Networking App 1.0 jar. Now, just like in the example before, we want to copy the application to the server and to the client. For that, let's use SCP. SCP, we want to copy the Sockets Networking App 1.0 jar to the server, which is VM RMI server. And we want to place it in home, Gene desktop. And the same thing for the client. And there we go. We have the socket app here in the server and here on the client. So let's run it. Let's change directory to the desktop. Java, parameter jar, and the socket networking app. If we provide nothing, it will tell us, okay, there's a missing param. So let's provide the param server. Simple server listening on port 12345. Now let's go to the client, change directory to the desktop. Java, parameter jar, sockets, client, and then the server name, which is VM RMI server. And there we go. We can see on both clients that they are connected to each other. So let's send a message, my message. And here we can see on both sides. My message received at the server side, and the server sent back my message in capital letters. And if we type bye, both sockets are disconnected. Now, obviously, you could add much more functionality than just bye. The only limit here, again, is just your imagination. You could, for instance, ask for any type of data. You could upload data if you wanted to, or you could provide commands that are calculated and the response is sent back. It really depends on what type of project you want to set up. So what we've just walked through is a basic example of client-server communication using sockets. On the server side, the simple server created a socket server that listened for incoming connection requests on a specified port. When a client connected, the server socket accept method returned a socket object representing the connection to that specific client. The server then used input and output streams associated with this client socket to read data sent by the client and send back responses. On the client side, the simple client created a socket to connect to the server's API address and port. Once the connection was established, it also used input and output streams to send messages to the server and receive responses. In this example, the communication was line-based, with the client sending a line of text and the server echoing it back in uppercase. The connection persisted until the client sent a bye command. This demonstrates the fundamental steps in socket communication. The server listens on a port, the client connects to that port, and then they can exchange data using input and output streams. Unlike RMI, which deals with remote objects and method invocations, sockets operate at a lower level, focusing on transmission of raw data. This provides more flexibility, but also requires the developer to handle details like data formatting, protocol definition, and connection management more explicitly. Sockets are the workhorses of network communication, forming the basis for a vast number of applications and higher-level protocols. Can applications built with different programming languages communicate over RMI or sockets? Alright, this is a crucial question that bridges the gap between Java-specific technologies and the broader world of multi-language applications. Let's address whether applications built with different programming languages can communicate using RMI or sockets. First, let's consider Java RMI. As we've discussed, RMI is deeply intertwined with the Java ecosystem. Its communication mechanism inherently relies on Java's object serialization to marshal and unmarshal data being sent across the network. This serialization process is specific to the Java virtual machine and its representation of objects. Furthermore, RMI's remote object management, including the creation of stubs and skeletons and the handling of remote objects, is also tightly coupled with the JVM. Therefore, the answer to whether applications in different programming languages can directly communicate over RMI is generally no. Both the server and the client applications need to be written in Java to understand and process the Java-specific data formats and protocols that RMI uses. While there might be theoretical ways to build bridges or wrappers, in practice achieving seamless and efficient cross-language communication with standard RMI is not feasible. RMI is designed for communication within the Java landscape. Now let's turn our attention to sockets. Sockets, as we've learned, operate at a much lower level. They provide a mechanism for sending and receiving streams of bytes over the network. The key difference here is that sockets themselves don't impose any specific language or object model on the data being exchanged. As long as both the sending and the receiving applications understand the agreed upon protocol for interpreting these bytes, they can communicate effectively, regardless of the programming language they are written in. This agreed upon protocol is crucial. It could be a standard text-based protocol like HTTP, where both a Python web server and a JavaScript web browser can understand the format of the requested responses. Or it could be a custom binary protocol, where both a C++ game server and a Unity game server client know how to encode and decode the game state information. Each programming language provides its own set of socket APIs that allow developers to create, connect to, send data through, and receive data from sockets. As long as both sides adhere to the defined protocol for the raw types being exchanged, successful cross-language communication via sockets is entirely possible and in fact very common. This interoperability is one of the major strengths of using sockets as a foundation for network communication in a heterogeneous environment. In summary, while Java RMI is largely confined to the Java world due to its reliance on Java-specific features, sockets offer a much more versatile approach that enables communication between applications written in different programming languages, provided they both understand the network protocol being used. Alright, we've reached the end of our deep dive into Java RMI and sockets, all sparked by those insightful questions from the comment section. So in this video, we started by unraveling what exactly Java RMI is, that object-oriented way for Java applications to talk to each other remotely. Then we laid the groundwork for sockets, those fundamental network endpoints that allow communication across different platforms and languages. We also took a moment to see what these two have in common, despite their differences in abstraction. And, of course, we got our hands dirty with some Java code examples to see both RMI and sockets in action. Finally, we've tackled the crucial question of cross-language communication, revealing the Java-centric nature of RMI and the language-agnostic power of sockets. Now, Mr. Rost Mohammed, I really hope this video shed some light onto your questions about data transfer in Java and across different languages. I also hope that I pronounced your name at least somewhere close to correct. If not, please feel free to educate my digital tongue in the comment section below. And for all of you watching, if you've got a burning question about Java or any other programming topic, don't hesitate to drop it in the comments below. You never know, your question might just be the inspiration for my next video. If you found this explanation helpful and maybe even learned a thing or two about distributed Java and network communication, consider giving this video a thumbs up. And if you're interested in more content like this on Java and other programming topics, don't forget to subscribe to this channel so you don't miss out on future videos. My name is Gene and it was a pleasure walking you through RMI and sockets. See you in the next video.